Hi, welcome back to Programming Foundations for Machine Learning. Today we'll be discussing about three of the most powerful deep learning frameworks in Python, namely TensorFlow, Keras, and PyTorch. You may have heard of this already because these are so popular, but if you are hearing about it for the first time, don't worry, we'll be discussing about these three in detail today, along with some implementation. So welcome to the lecture. At the end of today's lecture, you will have a fairly good idea about what is a deep neural network and how is Keras, TensorFlow, and PyTorch so important and so popular. We will build a very simple neural network using Keras as well as using PyTorch for a binary classification task. And we will also be incorporating scikit-learn in one of the code modules to import certain data set. We can also have a small discussion on when to use scikit-learn versus TensorFlow versus PyTorch. So with that, let's get into the lecture. So firstly, let us discuss what is a neural network. Very basically, neural networks are called as universal function approximators because a neural network with a single hidden layer with finite number of nodes can approximate any continuous function in a given range of inputs. So they are called as universal function approximators, but an even simpler way to think of neural network is as a bunch of layers. So you may have seen this kind of a figure, which denotes a neural network by its input layer, hidden layer or multiple hidden layers, plus the final output layer. So in this neural network, the one that you see on the board right now, there are three nodes in the input layer, meaning you can have three values as the input. There are two hidden layers. This is the first hidden layer, and this is the second hidden layer. And you have one node in the output layer. So there is a single number as the output. These neural networks are also sometimes called as large composite functions. And here, this neural network can be represented by a function like this. So output is equal to sigma of. So this is not sigma multiplied by, this is sigma of, where sigma is a function. W2 multiplied by sigma of W1x plus B1 plus B2. So W1x plus B1 is the linear transformation of this x as the input. Then a bias is also added. So W is called as weights, B is called bias, sigma is called as activation function. In this neural network, if activation function was not present, then the output would be, let's say, y equal to W2 times W1x plus B1 plus B2. And this can be expanded as W2 W1x plus W2 B1 plus B2. So now this can be thought of as a combined bias and this as the combined weight, and x is the input. So if you don't have activation function, this looks like the equation of a line, y equal to mx plus c, right? So what that means is, in the absence of an activation function, you can't approximate non-linear patterns in the input data using a neural network. And that is the reason why activation function is used. There are many types of activation functions. ReLU, rectified linear unit. There is Sigmoid. There is TANH. Then there is leaky ReLU. So there are many types of activation functions that can be used. So in our neural network that we are going to be constructing today, we'll be using mostly ReLU activation function. So we don't have to go into the mathematical details of these activation functions or the theory of neural network or the backpropagation, because the primary goal of this lecture today is to get you familiarized with the deep learning libraries and get you a hands-on flavor to hands-on implementation. So one small question that we can ask ourselves is, what's the difference between a neural network and a deep neural network? So a normal shallow neural network may have only one hidden layer, whereas a deep neural network can have multiple hidden layers. For example, a deep neural network like ResNet 101, it has 101 hidden layers, total layers. So it's definitely a very deep neural network. Now, with that, let's also discuss what's the difference between deep learning and machine learning. In what cases do we have to use deep learning versus in what cases do we have to use machine learning? So let's say we have a problem like predicting house prices. If you have the details of a house, number of bedrooms, its square foot area, and some other details like number of floors, etc. And if you have the corresponding housing price, and if you have this for 60,000 houses, you can make predictions on a future house, which may have a certain known number of bedrooms, known year of how old it is, known number of floors, etc. And we can try to predict the price of that house. For this, technically deep learning or deep neural network is not needed. We can also do this using a traditional machine learning model like regression. So this can be done using a traditional ML problem, the house pricing prediction. Whereas if you have an image classification problem like classifying cats versus dog image, here definitely a deep neural network is required, and ideally with convolution operations. So convolutional neural networks will be an ideal candidate for problems like this. Even a regular deep neural network may not be enough if convolution operation is absent. In one of the machine vision or computer vision courses that we have, we had seen that for a 5-class classification, even if you try to optimize a deep neural network as much as you can, in the absence of convolution, it's very difficult to get the neural network to get into 90-95% accuracy. You will reach 50-55% accuracy, but not more. If you want to perform a sentiment analysis from a text, again, you will need a deep learning framework, because this won't be a case of a traditional machine learning problem. Extracting features from text data is very difficult. For here, the features are the columns themselves. So if you have housing price as a function of the size of the house, the years, how old the house is, square foot area, number of bedrooms, etc., then those are the features. So features are already available. Whereas in image, the only available features are pixel values. The other features, which are features you can extract from combination of pixels, that will be learned during the process of training the neural network. Similarly, if we have text, you won't get features directly to be used in machine learning model. Rather, you can use a deep learning model, and that will hopefully extract relevant features from the text for sentiment analysis. If you want to perform just a linear regression on a simple data set, then you don't even need any deep learning framework. You can simply use linear regression from, let's say, scikit-learn. Scikit-learn is also a very popular ML library in Python. It makes your life so much easy to perform, let's say, implementation of KNN, K nearest neighbors, or let's say implementation of decision trees or regression models. So that's the difference between when you have to use ML model versus deep learning model. In today's example, we'll be implementing a deep learning model for a binary classification. So the remainder of this lecture is split into 2 parts. In the first part, we will look at TensorFlow and Keras and the difference between TensorFlow and Keras. We will also implement a simple deep learning framework using Keras TensorFlow. In the second part of the lecture, we will look at PyTorch. So first, let us look at what is TensorFlow and what is Keras. So Keras is a very user-friendly API. API is like something that you can call for executing a certain function, and it is built on top of TensorFlow. So TensorFlow is a deep learning framework in Python. Basically, it's a library which you can import, and it allows you to perform operations on data set. It allows you to define deep neural networks, highly custom deep neural networks, and it allows you to perform forward propagation, backward propagation, then predicting for test data. Every single thing that you can imagine with respect to deep learning, you can do using TensorFlow. It was originally built by the team at Google Brain for their own internal purposes, but now it has become open source and one of the most popular deep learning frameworks on Python. And Keras basically is an additional layer of abstraction which makes usage of features in TensorFlow much easier. So whenever you are importing Keras, you will be importing TensorFlow.Keras. So one of the advantages of TensorFlow is that if you have, let's say, calculations that can be performed in parallel, like maybe training a neural network on different batches of data, you could do that in parallel. One of the advantages of TensorFlow is that it allows you to make use of GPU. So if you look at the way Python has evolved, initially Python had lists, and these lists could store array of numbers. But here, if you wanted to perform operations, you could not perform vectorized operations. Let's say you wanted to calculate dot product between two lists, you had to loop from first element all the way till the last element, and this was very slow. Then NumPy was introduced, and NumPy made vectorized calculations so easy, which means if you execute, let's say, a vector dot product using Python lists versus NumPy could execute it much faster. But NumPy was primarily based on CPU. So you could not leverage the, faster calculations even with GPU. But you know that GPUs were invented with the goal of making matrix multiplications much faster. You could perform parallel computation, and this kind of caused the entire AI revolution to happen. And this is also one reason why NVIDIA has skyrocketed in its valuation. Originally, it was meant for gaming to render graphics, but now it's mostly used for AI model building, training, and inference. So in TensorFlow framework, if you have the same NumPy array as a TensorFlow tensor, if GPU access is there and if GPU execution is possible, the calculation will be much faster. So this is one of the reasons why people prefer TensorFlow data over NumPy data. And if you want to think of the difference between Keras and TensorFlow, Keras you can think of as the front end with which you can interact, and TensorFlow you can think of as the backend engine behind it. So the framework of deep learning is defined in TensorFlow, but Keras makes it easy to interact with it. This is very much like NumPy. So NumPy is mostly written in C or C++ rather than in Python, but it provides a very nice front end in Python to interact with the NumPy library, although it is primarily written in C or C++. So similarly here, Keras makes it very easy to use TensorFlow, but most of the definition of functions and classes, objects are all done, classes are all done in TensorFlow. All right. Now with that, let's try to implement a very simple binary classifier using TensorFlow Keras. All right. So first, the data. So what we are going to do is, I have split the code into different chunks. So defining the data, then training the TensorFlow model, then plotting the data plus the results. And finally, what you will see is something like this. What we have is binary data where all these blue dots belong to class 1, all these red dots belong to class 2. And we will train a binary classifier neural network to get hopefully decent validation accuracy. It's something that looks like this, 90%, close to something like that. So now what I'm going to do is, let's open Google Colab and let's try to implement this code block by block. So open Google Colab by typing colab.research.google.com and just open a new notebook. And here what we can do is first, let us import the required libraries. So the libraries are, we need NumPy. We'll be using matplotlib for plotting. We'll be using scikit-learn for getting the trained test splitter. And of course, TensorFlow. So let's copy the import part and let's paste it here. And I'm going to name this as deep learning libraries. And let's execute the code. Nothing will happen because it's just importing the files. After this, let us generate a 2D binary data set. Basically, it will have two features, X and Y. So number of features is 2. Total number of data points are 500. And let's just copy this. And this random state defines the repeatability. So if you use the same random state while generating the data set, which is random, you will be able to repeatably execute the code. If you don't use random state, you won't be able to get exact same result. All right. So now importing is done. So now let's generate the data set. So this creates the classification data set. And you can see that this make classification function is imported from scikit-learn.datasets. Then this sklearn is scikit-learn, and this model selection allows you to access train test split. So we'll be splitting the whole data set into 80% for training and 20% for testing. Here there is another function, standard scaler. So basically the data set has to be scaled such that mean value is 0 and standard deviation is 1. Here is an example of data set in ML. So you can see like there is a graph. Yeah, for example, this graph denotes how the scaling works. In fact, if you type batch normalization, a nice graph shows, which denotes the idea of scaling. Batch normalization visualized. So this is the plot. In this plot, you can see initially the data set has non-zero scaling along, like you can see that along x-axis, the range is more, along y-axis, it's shorter. So feature 1, feature along x is bigger than feature along y in terms of the scale, visual scale. The second issue with the data set, the second issue with this data set is that before scaling is that the mean value is not at the origin. So after scaling, you can bring the data set such that the mean value is at origin and standard deviation is 1, so that the scaling is appropriate along all the features. So this we can do to the data set by using the standard scaler function. And then after we have the scaled data, we can perform the train test split, where it will create the data as well as the labels. So X train is the training data, Y train is training label. This is the training test data, and this is the test label. So this can be created using the train test split function. Now, once this is done, we have the code for defining the TensorFlow model. So here we use tf.keras. So in tf.keras, we use the sequential function. So what we can do is copy this code and paste it here. So tf.keras.sequential allows you to define the layers of the neural network sequentially. So the first layer here is a dense layer with input being 2, and in between the hidden layer has 10 nodes, and there is a ReLU, rectified linear unit activation function. The final output layer has only one node, and the activation function that is used is Sigmoid. So Sigmoid will look like this. Here, the range of Sigmoid on y-axis is from 0 to 1. And I don't know why these biology images are coming. Sigmoid function. So here the range is from 0 to 1. And you can say that if the value of sigmoid function is above 0.5, then it belongs to class 1. If it is below 0.5, it belongs to class 0. So this is the way in which you can classify a binary data set using sigmoid. We are using optimizer Adam. There is vanilla gradient descent. There is stochastic gradient descent. There is momentum-based gradient descent. There is root mean square propagation, and there is Adam. Adam combines the best of RMS prop and momentum. And we have binary cross entropy loss as the loss function, and we'll be tracking accuracy as the metric. Then this model.fit function is called over the the training data set, training labels. We are running for 30 epochs, so total 30 iterations. Batch size is 16, meaning one batch of data will have 16 data point, and 20% of the data will be used for validation. So now let's execute this. This will run the 30 epochs, and you will see the variation of the training accuracy as a function of epoch that will be displayed here as the code is executed. So here you might be wondering, why are we classifying data set with just 2 features using deep learning? Why can't we use machine learning framework for this, like normal decision tree or random forest? Of course, we can use that. But here I wanted to keep the deep learning, the deep neural network very simple. That's why I went with this data set. But here you can see that for that reason, this accuracy is already very high. In the first epoch itself, accuracy starts at 0.77, so 77%. Validation accuracy is 86%. And then you can see that after 30 epochs, it reaches close to 90%. So fairly good accuracy for this data set. Now what we can do is we can visualize this whole data set plus the results in a graph. So let me run this part of the code. So the first plot is done using PLT. So PLT is from import. matplotlib dot pyplot as plt, right? And I think we had already done that. Yeah, so we had already imported it. So this line of code is not needed here. Let me delete it. And plt.figure. So let me only run the first part of the code. So this will define the figure where you can see the data set. The first class is this red, second class is blue, and there are two features. So it's like a two-dimensional data set. Then after that, we can also execute the code which shows the accuracy as a function of epochs, training accuracy and validation accuracy. So now you have two plots here. Training accuracy is around 90% plus, validation accuracy goes till around 94-95%. And this is a pretty good model. And that's what we have plotted here as well in the notebook. So I'll share the code with you. Just try executing it and see how much accuracy you can get. One more experiment that you can do to make this problem a bit more complex is increase the number of features. Then obviously classification might become difficult. And one more thing you can do is after you increase the number of features and the number of classes, you can also do increase the number of layers. So here you can define more dense layers. Maybe you can add one more dense layer with activation being ReLU. Input shape will obviously depend on the output from the previous layer, right? So that is what you can do to make this more complex. Now with that, let's get into PyTorch. So we discussed Keras and TensorFlow. Now let's look at this will be the second half of today's lecture. What is PyTorch and how to implement deep learning framework using PyTorch. So PyTorch is an open source deep learning framework in Python developed by the Facebook AI research team. It's also very popular and heavily used in academia as well as in industry. And one of the main advantages of PyTorch is that you can build more custom deep neural networks compared to Keras. So if you want simplicity, go with Keras. If you want more custom models to be built, you can go with PyTorch. So let's see how PyTorch implementation can be done. So basically, the key features of PyTorch is that it has, again, the tensor data set, which is much better than NumPy array because NumPy does not have GPU support. Tensor has GPU support. There is this base class in PyTorch called nn.module, neural network.module. So when you are defining your neural network, you will be using nn.module. There is the forward function, which shows how the data flows from one layer to the another. The torch.optim module has optimization packages like stochastic gradient descent, momentum, Adam, etc. And there is autograd for automatic differentiation. So if you want to find the derivative of the output with respect to something, basically you will be differentiating the neural network itself, and that can be done using this autograd function. So this will be very useful if you want to implement frameworks like scientific machine learning. In a concept called neural ODE, the neural network is supposed to predict the gradient of an ordinary, like gradient of a parameter, which will be basically the replacement of an ordinary differential equation. So these are some of the most prominent concepts in PyTorch, but let's keep it very simple today. We'll implement a simple PyTorch model with two input features. We have two-dimensional data, right? X and Y. And we had 500 data points randomly defined. There will be one hidden layer and one output layer with Sigmoid activation. So basically exactly same as TensorFlow. So here again, first step that we do is we import the required libraries. So we can write the code in the same file that where we were writing our code for TensorFlow. So we import torch. So this is PyTorch, and torch.nn is where you get access to nn.module. Then torch.optim is where you get the optimization. Scikit-learn you are using for datasets. So scikit-learn you can write separately. Matplotlib for plotting graph, NumPy for NumPy array and mathematical operation. And scikit-learn.metrics is where you can get the accuracy score once you have the predictions. So now with that, let's just implement the importing. It won't show any output. It will simply import the libraries. Second step is preparation of the data set. Here again, we are calling the exact same function called make classification with random state 42. So the data set will look exactly same as what we had before. Like what we had before was this. So data set will look exactly the same because the random state that we are using is the same. If we change the random state, data set will look different. But there'll be 500 samples, 2 features, so 2-dimensional data and 2 classes. And we'll be scaling the data based on the fact that we need mean value to be 0 and standard deviation to be 1. And then what we do is we convert the data set into PyTorch tensor. So PyTorch tensor means if you have access to GPU, your computation can be much faster, unlike NumPy array. So here, this X-train, X-test are the input X data sets, and Y-train, Y-test are the labels. Now let's visualize the data set. So after visualization, you will see that it's exactly same as the previous code. And I will show you the data set, how it looks after we change the random seed. Instead of 42, we can choose some other random seed. So here, just have a look at the data set. This one is exactly same as before, but let's change the random state to maybe 20, any number, and let's plot it. You can see that hopefully there is minor differences. Maybe what we can do is change it to some big number. I don't know what makes a difference, but we'll see. So there will be, let's take a screenshot of the previous data and put it side by side to make sure that there is some difference. There has to be some visible difference in the data. Okay, so this is the previous data set. In fact, the current data set looks exactly the same as before. Let me check if something is correct or not. Okay, my bad. I had not updated the random state here, the data set generation. So hopefully now so now it looks completely different. Okay, very good. So this is the new data set because the random state was changed. So if I change this random state to 20, I'm sure this will look different from before. Yeah, it definitely looks different. So this is the new data set that we generated after scaling. Of course, the mean value is 0 and the standard deviation is -1. Here also mean value is 0. Standard deviation is, not -1, standard deviation is 1. Now we can define the neural network using nn.module. So if you remember, we had imported nn from PyTorch, so torch.nn. So nn.module is very much used. So here the input layer has dimension as the input dimension, and input dimension will be used wherever we are calling this, wherever we are defining the object. Then the hidden layer has 10 nodes, output layer has 1 node, and then we are defining activation function. So activation function in the 10 node hidden layer is ReLU, and activation function right after the last layer is Sigmoid. So exact same structure as what we defined using Keras. In Keras, this exact same thing was done using sequential function, keras.sequential, TensorFlow.keras.sequential, this one. So both are doing the same thing, except it's 2 different ways of defining the neural network architecture. Now what we do is we can initialize the model. So we are creating a model using this simple NN class. So this is now an object, and input dimension we are defining to be 2. Why 2? Because in our data set, it has X and Y features. And we are defining the loss, and then optimizer is Adam, and learning rate is 0.001. So let's run the model. Simple NN is not defined. Okay, now it should be fine. That was because this block of code was not run. Now we have the manual training loop where we train the neural network for 30 epochs. So number of epochs equal to 30. We define empty arrays for training accuracy and test accuracy and loss, because we are going to plot all of them. And then we say we have a for loop for epoch in range of number of epochs, which is 30. We call model.train. So model.train, and what is model? Model is the object which is based on this simple neural network class. And then when we call that, training happens and output is equal to model of X underscore train underscore tensor. So now this will be passed into the model, and loss is defined based on loss criterion, and the outputs are over here, and you will be comparing the output with the Y values. So Y values are the labeled training data labels, which we converted into PyTorch tensor. Then we call optimizer and loss function, and we go one step. So this is the backpropagation step over here. And once this is executed, we have the prediction for training data as well as the test data. So training data prediction is if the output is greater than 0.5, then the class is 1. If the output is less than 0.5, it is 0, because at the output we have Sigmoid activation function whose range is from 0 to 1. And then we calculate the training accuracy based on number of correctly predicted output. So that is done using this accuracy underscore score function. Then similarly, we get test accuracy, where we use the model and pass the test data set, and we compare the predicted values with the and predicted values is converted into a threshold above 0.5 class 1, below 0.5 class 0, and accuracy score function is again called with y underscore test underscore tensor. So this is the tensor test data set, and then this is the actual predicted data set. It's converted into NumPy so that it's easy to compare. And this accuracy underscore function is called, or like it's over here, accuracy underscore, which was called from the scikit-learn.matrix. So we'll be using that. So here are the outputs. The output accuracy goes all the way till 0.89 for training and 0.87 for testing. In the previous case, it was 0.89 for training and 0.93 or 94 for validation. So very much close, but I think validation accuracy was better with the previous machine learning model we defined using Keras. Here it is different because we have different initial input. When I say initial input, I mean the random number. So random number generator had the 42 as the seed. So let me keep this as 42 instead of 2000. So this will be 42. Here also, let me keep 42 as the random state. So hopefully we should get somewhat repeatable results. So data set is now looking like before, and definition of the neural network, definition of the model, 30 training epochs. And I think accuracy is still pretty much like what it was before. And now let's plot the accuracy. So loss is decreasing from 0.75 to 0.45. Here is the training accuracy, test accuracy plot. Both are close to 0.87, 0.88, that range. Previously, we had something like 0.87 for training and 0.9394 for validation. So it's very similar. And we also can have, I think that's it. So we don't have any more plots. So training loss, training accuracy, validation accuracy, and the initial data set distribution in the scatter plot. So this is a very simple implementation of deep learning model using PyTorch. So today we learned three things. What is Keras? What is TensorFlow? So Keras is almost like a front end for the TensorFlow. TensorFlow is the backend engine. Then you also implemented a PyTorch model. So what I recommend is I'll share the code with you, but implement the code block by block yourself in your Google Colab notebook. You can also take a copy of the Colab link that I provide and you can try executing. But this will be a very good introduction into Keras and TensorFlow and PyTorch. What I also recommend is try with a more complex data set. You could try an image classification. It will not work very well because we have not defined any convolution operation. Otherwise, what you can do is you can increase the number of features, and then if the model is not performing well, increase the number of layers and see if you are able to bring the accuracy from a poor accuracy to good accuracy. Here for us, we already have decent accuracy, which is why I'm not performing hyperparameter tuning. But with that, let's come to an end to this lecture. And I hope to see you again in another lecture. Take care until then, and bye. So I really hope you will try implementing what you learned in this lecture on your own Google Colab notebook. So thank you so much once again, and take care. Bye.